Welcome to part 4 of week 5 of the class Neuronal Dynamics. In the previous lectures of this week, I focused on experimental data showing fluctuating membrane potentials and fluctuations of spike timing. We now turn to a first model that should allow to explain the observed fluctuations of the membrane potential. We have seen that fluctuating membrane potentials can be observed in a randomly connected network of leaky integrating firing neurons. Let's now take one of the neurons. We have here our big network of neurons. Let's just arbitrarily pick one of the neurons, say this one here, and say this is my special neuron. I will consider the input to this neuron. Now, from the point of view of this neuron, what this neuron sees are spikes, and the spike arrival looks stochastic. So, we consider the input to this one neuron. It's not a special neuron, it's an arbitrary neuron of the network, but for us it's a special neuron, because we look at its input. Now, here's the spike train that this neuron may see, the total spike train arising from K presynaptic neurons. Let's describe this spike train. Any pulse occurs at some firing time, TF. Now, this might be a pulse arising from neuron number K. So, I have a short pulse described by a Dirac pulse, S of t, TKF. Now this neuron will send out many spikes. I sum over all the different spike times. And then K is just one of the neurons. There's a total of capital K neurons that send inputs to our neuron that we observe. So far, the observed spike train. I said previously that from the point of view of this neuron, spike train looks stochastic. So let's take our Poisson model. Let's assume that each neuron, each of the K neurons, fires at a constant rate, rho 0. Then the total probability that one of the bins here is filled with a spike is the firing rate of each individual presynaptic neuron times K, the total number of presynaptic neurons. So we can now ask, with our spike train, what would be the probability of observing a spike in this short time bin? Well, if I have a time bin, then this is the probability that I observe a spike arrival, by definition of the Poisson model. When I take the limit delta t to 0, I can ask, what would be that instantaneous firing probability? Well, I take delta t to 0 and I divide by delta t. So, divide by delta t, take delta t to 0, then we sort of are back to our spike train. We just have pulses, and I ask for the expectation. This is the expectation sign. I ask for the expectation that I would see these spikes. Well, the expectation of having a spike at each moment of time is the rate. I have a total of K neurons, so this is K times rho 0. So the firing rate of a Poisson model can be estimated from the spike train by looking at the expectation value and the experimental procedures of estimating a rate, be it population averaging or trial averaging, are approximations to this mathematical averaging sign. I have this spike train, and I assume that spike arrival is Poisson. I'm interested in the current that would flow into this neuron. So the total current that this neuron sees. Well, let's assume that each of the spikes, this spike here for example, causes a response. If the spike occurred at time TF, and it happened to be from neuron K, then this would be the response. I describe this response as a function alpha of t minus TKF. So this function is the current injected after the spike arrival injected into the neuron. But now comes a second spike. And the second spike contributes a similar current pulse. The third spike contributes a current pulse. The fourth one, the fifth one. And I have another two pulses. So the total current is the sum of all these current pulses. I have to sum over the different neurons. I have K presynaptic neurons. And then each neuron may send out several spikes. So this might be the first spike of neuron K. Here might be the second spike of neuron K. I have to sum over all firing times of this neuron K. I can now ask whether I can make any statement about this current. So what I see is essentially that this current fluctuates around some mean value. So the mean would be something like the expectation around this current. So I have to calculate this expectation. How would I do that? Well, sometimes things will become simpler if you first make it look more complicated. So let's write this in a slightly more complicated fashion. I say this is the same as, but I introduce an integral, alpha of s, and then I say delta of t minus TKF. Minus s ds. So if I integrate this delta function, I'm back to the situation here. Well, the summation signs can go inside, so I have here sum over k, sum over f. Now let's add the averaging signs. I'm interested in the mean current, mu. The averaging signs, well, what is stochastic here? Stochastic are the spike times. They may have a jitter. The spike may occur in this pin or in that pin. This spike may occur everywhere. So the stochasticity over which we average is just in the spike train. It's in here. I can pull in the averaging side inside the integral. Now, this is my spike train, S of t minus s. The definition of the spike train was a sum over all these different spikes, the sum over the delta functions. But the expectation of the spike train under a Poisson model is just rho. Suppose I have a homogeneous Poisson process, so this gives rho 0, and I have a result, mu is the average of my current. It's constant in time, and the result is alpha of s ds times rho 0. So what we did is we pulled out an arbitrary neuron. We looked at the input current into this neuron. I have these pulses alpha. Each pulse describes an excitatory postsynaptic current. Excitatory in our case. It could be an inhibitory current, then it would be IPSC. So let's stick to the EPSC. The result of this is some fluctuating current, and I'm able to calculate the expectation value of this fluctuating current. And this gives a mean value, which I summarize as I0 plus a fluctuating part. So what this neuron sees here is an input current, a total input current. That's just a fluctuating current, fluctuating around some mean value mu. And so in that sense, a neuron embedded in the network is very similar to an isolated neuron driven by a fluctuating current with a certain mean mu and a certain variance of the fluctuations called sigma. So this is the input current. Now suppose that our neuron stays in the subthreshold regime. So the neuron can be described as a passive membrane. I have a leak term and I have an input. The input comes from the synapses. The input is exactly this guy here, the synaptic current, which I can write like this. This synaptic current has a mean part and it has a fluctuating part. This fluctuating current is injected into the neuron and will cause a response of the membrane. I inject this current into a neuron. Suppose I start here. It's a fluctuating current. It will go up and down. And the membrane acts like a low-pass filter on this fluctuating input current. So if I plot here the membrane potential U of t, then I can ask again, what is the mean of this membrane potential? Let me sum up a little bit. So we did this calculation of estimating a mean under the assumption of a Poisson process by rewriting it with delta functions, which essentially means I put in a spike train and integrate over the spike train. The reason is I can now perform the averaging. Averaging over the spike train just gives the rate. Now, I said Poisson process. It could be a homogeneous Poisson process, like in the calculation we did before, or it could even be a inhomogeneous Poisson process. And the calculation would be just the same. In that case, it's a time-dependent estimate. For a Poisson process, it's a constant, and this dependence can go away. Note that there are two different ways of writing the integral, as we have seen in the first week. I can also integrate with t minus t prime and start from minus infinity up to t. Now this mathematical procedure is independent of the details. Suppose I have some arbitrary variable x of t, which can be described as a filtering process and some point-like events, pulses, for example a spike train, then the average is just the average of the pulses integrated with that filter, and this average now for the time-dependent model, inhomogeneous Poisson process, is the time-dependent firing rate. In the specific case at hand here, I allowed here that different neurons have different weights. So some neurons might cause a large current pulse, other neurons might cause a smaller current pulse. Different synapses have different weights. Now, this kind of formula can be used not just for calculating the mean synaptic current, but also for calculating the mean potential. Let me summarize. A neuron embedded in a network will see a barrage of spike arrivals. And spike arrivals look stochastic from the point of view of that neuron. Under the assumption of Poisson-like stochastic spike arrival, we can calculate the mean input current, the fluctuating part of the input current, and also the mean potential and the fluctuations of the potential. A first step of this calculation for the potential is part of the homework assignment.